Okay, so we're looking at 2011 extension 1 HSC paper, extension 1, and we're looking at question 3b. And so question 3b is a parametrics question, and if we're going to find the tangent, then we need to start by finding the gradient. So the function that the tangents come off is y equals x squared, which means we're looking for the gradient function dy dx, and that is 2x. And then at p, we have t comma t squared, and therefore the gradient at p, dy dx, is equal to 2t, because t is the x value. And so that's the gradient. Then if we're finding the equation of the tangent, then we make it gradient intercept form. So we've got y minus t squared equals m, which is 2t outside of x minus t, which is the x value. Expand that out, you get y minus t squared equals 2xt, or 2tx minus 2t squared. And when you plus t squared to both sides, you get y equals 2tx minus t squared, as required for part I. Okay, then for part II, it asks us to write down the equation of the tangent to the parabola at Q. So at Q, we have 1 minus t, comma 1 minus t in brackets squared. And so dy dx at Q is equal to 2 lots of 1 minus t. And therefore, in gradient intercept form again, y minus 1 minus t all squared equals m, which is the gradient, so that's 2 outside of 1 minus t. And that's the gradient, so that's multiplied by x minus x1, which is the x value, which is 1 minus t. Put that in a bracket so you don't get confused. So, in expanding this out, in a similar way, you could actually go straight from using the previous one if you recognize the 2t pattern. But if you can't, you can just expand this as normal. You would get y minus 1 minus t squared equals, and I'm going to times in here and get 2 outside of 1 minus t x. So that's the first one expanded, minus 2 outside of 1 minus t all squared. And so that gives us y equals 2 outside of 1 minus t x minus 1 minus t squared, as we bring that other one from the left across. And you can see that where there was a t in the original equation, y equals 2tx minus t squared, in place of that t is a 1 minus t, and so the pattern is almost identical. Okay, so part 3, it asks us to show that the tangents at P and Q intersect at R, and they give a value of R. Now, for the tangents to intersect, we need their x and y values to be the same simultaneously. And simultaneous is the key word in that sentence, whereby we're trying to solve it. One way of doing that would be, because they're already in the form of y equals, you can make them equal to each other to find the x value. So we can do that. And you can actually simplify this. So we've got equation number 1 is from part I, and equation number 2 is from part 2. And because they're both y equals, we've got 2tx minus t squared equals 2 outside of 1 minus t x, and minus 1 minus t squared over there. We'll get a pretty messy value for x here, but it will clean up slightly if we expand out just the first bracket. So we get 2tx minus t squared equals, now I'm expanding this to get 2 times 1 times x, which is 2x, 2 times minus t times x, which is minus 2tx, And then I'm going to expand this out as well carefully. So minus 2t, but there's a minus out the front, so it's plus 2t, and plus t squared, but with the minus out the front, it's minus t squared. Okay, so grouping everything together, you've got a minus t squared on both sides, which cancels. So then you've got also negative 2tx on the right-hand side, so add that across, and you get 4tx on the left-hand side, minus 2x, and then you've also got on the right-hand side, you've got left over a 2t minus 1. Then I'm factorising x out to solve, and I get x outside of, or I should say 2x outside of 2t minus 1 equals 2t minus 1. Then I'm dividing both sides by 2t minus 1, and I get 2x equals 1 and x equals a half, which is the x value we were expecting, because that's what we were asked to show. Then in addition to that, you can sub in the x value to find the y value. The easiest place to sub that in is to equation number 1. So in equation number 1, we get y equals 2tx, which is a half, minus 2t, just t squared, not 2t squared. 2 times a half is 1, and you get y equals t minus t squared as required. So therefore the point of intersection which is R is at a half, comma, t minus t squared as required. Okay, and then the final question asks us to figure out the locus, and basically when we're asked to find the locus, we're looking at finding the Cartesian equation. We've currently got the parametric equation, which is R is half, comma, t minus t squared. And so the first step always in solving one of these problems is to write down in Cartesian form. So we've got x is equal to a half, and we've got y is equal to t minus t squared. Now, as you can see, the definition of that, okay, so because x is equal to a half, it's a constant, which means it's unchanging. And when a letter is constant, that means you're going to get a line, either a horizontal or a vertical. And because it's x equals to half, you're going to get a vertical line, because the x coordinate is always a half, which is a straight line up and down from half. So it's a vertical line at x equals to a half. Now, they ask for restrictions on the y coordinate, and the reason for that is because the y coordinate can't actually be anything. It does have restrictions, and the reason it has restrictions is because the function y equals t minus t squared means that t has a maximum value. And the reason it has a maximum value is because it's negative t squared, which means it's concave down. So y is equal to t outside of 1 minus t, and that has turning points at t equals 0. Sorry, it has zeros at t equals 0 and t equals 1. So if the two zeros are at 0 and 1 and it's just a normal parabola, then the maximum will be halfway between, because the vertex is halfway between the zeros, because a parabola is symmetric, which means that t is equal to a half, because it's halfway between 0 and 1. So because that has a maximum value of t, it also therefore has a maximum value of y. Y can only be a certain number of values. And because it's restricted to meeting t minus t squared, we're subbing in that t is equal to a half. And when t is equal to a half, you get y is equal to half minus half squared. So, because that's the maximum value of t, that also happens to be the maximum value of y. It's not the maximum value of t, it's the value of t which produces a maximum value of y, and the maximum value of y is 1/4, or a half minus a quarter, which is a quarter. So because that's the maximum value of y, the restriction is that it's a vertical line at x equals a half, and y is less than a quarter, because remember that's the maximum value of y. So that means that the vertical line actually stops. So if we were to graph that, which I'll do up in the top corner so you can see, we've got a vertical line at x equals to a half going down like this, but it actually only exists for values of y that are less than or equal to a quarter. So it's a vertical line like this with a closed circle because y is allowed to be equal to a quarter. And that's it.